আমার কথা শোনা যাচ্ছে?
Yes, madam.
So far what we have discussed is basically on cylindrical rotor machine. So I'll start salad pole machine today. Now this is the basically phasor diagram of a cylindrical rotor machine. So this is the terminal voltage VT and lagging current IA. So machine have some armature resistance, so there will be a IARA drop and IAXAL drop, that is a leakage reactance drop. So the terminal voltage plus these two drops is the air gap voltage or the induced EMF under running condition, loaded condition. Now, if we start from the field excitation, then the field excitation, this is the reference. So FF, this induces an EMF EF. This is the induced EMF or the open circuit voltage. So this is the terminal voltage and the open circuit condition. Now, when the machine is loaded, carrying a current IA, so neglecting saturation, the armature reaction will be proportional to IA. So FA is in phase with IA. So now we have two MMF, the excitation MMF EF and armature reaction MMF FA. So the resultant MMF FR is the vector summation of these two. So under loaded condition, what exists is the resultant MMF FR. So this induces the EMF ER or the air gap voltage under loaded condition. This minus the leakage reactance and resistance drops gives you the terminal voltage. This difference between EF and ER, this is IA, XAR or the voltage change in voltage due to armature reaction. Now in this phasor, we have just simply added all the phasor quantity by phasor summation method. That is because we considered a cylindrical rotor machine. So basically its air gap is constant. So if we can consider a sinusoidal excitation, if the MMFs are sinusoidal, then and we have a constant reluctance. So MMFs by the reluctance give you a sinusoidal flux. So corresponding EMFs are also sinusoidal. So all quantities are sinusoidal. So we can simply add them by vector addition, or I treat them as sinusoidal vector quantities. Now, this is not the case in case of salient pole machine. In salient pole machine, what happens? Now, actually, the nature of the flux will depend on the power factor. The form of the flux form will depend on the power factor. Say if we consider a current IA which is lagging EF by 90 degree. So this is our EF excitation MMF which is inducing an EMF EF lagging it by 90 degree. Now the current which is flowing IA, suppose it is lagging EF by 90 degree. So FA is in phase with IA. So FA divided by the reluctance of the flux path will give you phi A. Now, if we draw the figure, here we have salient pole structures. So poles are projected like this. So the air gap in this region, pole region, is not same as the air gap in the interpolar region. This is called the direct axis, the pole axis. The interpolar axis is the quadrature axis. So air gap along the direct axis and quadrature axis is widely different, and so the reluctance is also different. Now, however, when the current is 90 degree lagging, then say if this is phi f, this is the considering a sinusoidal flux, then FA, if the current is sinusoidal, FA is also sinusoidal, it is 90 degree away. So this will be your FA. Now the reluctance, the flux is maximum in this polar region. So in the polar region, air gap is small. So only here the air gap is large. So approximately almost the flux will, except in this region, the flux will follow the MMF wave. So it is approximately a sine wave. Now this is for lagging current. If we have a 90-degree leading current, the same thing will happen. The flux will be here demagnetizing, it will be magnetizing in nature. Now, however, if we have a current which is in phase with EF, then what happens? This is again the flux form what we considered earlier. But now if A is in phase where 90-degree different from FF. So FA is 90-degree away. So it is maximum here in the interpolar zone and minimum in the polar zone, or zero at the direct axis, maximum at the quadrature axis. Now what happened? The flux is MMF divided by the reluctance. Now reluctance in this polar region under the pole is more or less constant and small, but in this region it is quite large. So where in this region flux is large, but the reluctance is quite large. So even that flux divided by the reluctance, MMF divided by the reluctance will give you a small flux. So in the polar region, that is from this point to this point, the flux will follow more or less the MMF wave. In this region, this is small, very small. Again, it will follow the MMF wave. So the effect is that it is highly distorted. The resultant flux will be the summation of field flux and the armature reaction flux. So the resultant flux will be highly distorted. So the effect of the current, which is 90-degree to the induced EMF, will be either magnetizing or demagnetizing depending on the power factor. The effect of the current, which is in phase with EF, the corresponding armature reaction, the effect will be mainly distortion. It is a cross-magnetizing effect. So the quantities are no longer simple sinusoid, or simply we cannot add this the quantities like this in the case of cylindrical rotor machine. Now in this case, to develop the phasor diagram of the salient pull machine, we uh, take into we consider a theory called two reaction theory proposed by Blondel. What is done? The current IA, or the armature reaction MMF FA, is resolved into two components, one along the direct axis and one along the quadrature axis. That is, we have the current IA. So this can be resolved into two components, one along direct axis, one along quadrature axis, as the summation, vector summation of these two ID and IQ is equal to IA. Similarly, FA, or the armature corresponding armature reaction, also can be resolved into two components, FA D and FA Q. So the summation of these two is FA. However, as the reluctance is not constant along the quadrature axis and direct axis, so the ratio of the flux, direct axis, quadrature axis flux, that phi AD by phi AQ is not equal to FAD by FAQ. But in case of cylindrical rotor, they were equal because the reluctance was constant. Now, as we resolve these into two components, it is assumed that this current ID creates MMA, armature reaction MMF FAD, whose effect will be mainly magnetizing or demagnetizing. FAD by the reluctance along the direct axis flux path will give you the FAD, phi AD, or the direct axis that flux due to armature reaction in the direct axis. Similarly, FAQ divided by the reluctance in the quadrature axis give you phi AQ. The ratio will be different. Now, effect of this armature reaction FAD will be mainly magnetizing or demagnetizing, and effect of FAQ will be distorting. Now, any current can be divided into two components, and we can dissociate them and take them their effect independently. Now, when we consider only the direct axis current and direct axis MMF, there that reluctance we can consider constant in the direct axis. Similarly, it is constant in the quadrature axis. Now, as in case of synchronous reactance method for cylindrical rotor machine, we assume that each MMF induces an EMF lagging it by 90 degrees. So FAD will induce an EMF EAD lagging it by 90 degrees. So EAD, it is EAD is equal to minus JKD FAD. KD is proportionality constant depend on the direct axis air gap, and air gap characteristic, corresponding air gap characteristic. Now, if we neglect the saturation, then FAD is created by the direct axis current ID. So we can write JCKDID is equal to EAD, which can be written as minus JXAD into ID, where XAD is the reactance which takes into account the armature reaction along the direct axis. Now EAQ similarly is minus JKQ FAQ is equal to minus CKQ FAQ, where considering FAQ is proportional to C KQ IQ, considering FAQ is proportional to IQ. So it is equal to minus JXAQ IQ. So XAD and XAQ at the axis and XQ axis armature reaction reactants. XAD takes in care of the armature reaction along direct axis. XAQ takes care of the effect of armature reaction along the quadrature axis. Now EAR, the air gap voltage is equal to VT plus IARA plus JIAXAL. And similarly, EAR is equal to summation of this, that is EF plus minus EF plus EAQ plus EAD. And IT plus IQ is equal to IA. So JIAXL drop that is in this equation can be written as JIDXL plus JIQXL. So we have VT plus IARA plus JIAXL is equal to EF plus EAD plus EAQ. So EAD is minus JXAD and this is minus JXAQ and this this is IAXL is IDXL plus IQXL. So if you take these two on this side, now this and this have the same dimension. So if we add XA P and XAL, we can call it XT, and this is XAL plus XAQ, we call it XQ. So our voltage EF will be, induced voltage EF will be VT plus IARA plus JIDXT plus JIQXQ. Now this XT and XQ are called the direct axis synchronous reactance and the quadrature axis synchronous reactance respectively. So in case of cylindrical rotor machine, we have only defined only one synchronous reactance, and our VT plus IARA plus JIAXS was equal to induced EMF EF. Here instead of synchronous reactance X's, we have find two synchronous reactances, the direct axis synchronous reactance XD and quadrature axis synchronous reactance XQ. So if we draw the phasor, it will look like this. That is, this is our VT plus IARA plus JIDXD plus JIDXQ is equal to EF. Now, if we neglect RA, as RA is very small, the simplified diagram will be like this. Now, the angle between BT and IA is theta, and angle between EF and BT is delta, or the load angle. So your ID is this component, will be IA sine of delta plus theta, and IQ will be IA sine of cos of delta plus theta. This is for the lagging power factor current. If it is leading, this plus sign will change. Now, one thing you can note that in this phasor, the first one for the cylindrical rotor machine, here uh, the measurable quantities are terminal voltage Vt, current Ia, angle between Vt and Ia, theta, the parameters Ra, and this total XS, synchronous reactance. So knowing this, we can draw the phasor diagram. That is, we take the voltage as the reference with current at a phase different theta degree away from terminal voltage. Then we can add resistance and drop related to resistance and synchronous reactance, and we will get EF. So it is possible to draw the phasor diagram from the measured data, and from there approximate regulation also can be calculated, though that is not very accurate. But in this case, that is for salient pole machine, it is not possible to draw the phasor diagram with the measurable data. That is because what is measurable here, it is measurable here is Vt, current Ia, the angle theta. Ra is measurable, so IARA known. XD and XQ, that is measurable, we can determine in the laboratory. But what is not known is the angle delta. That is the load angle between Vt and EF. And unless delta is not known, we do not know the position of direct axis and quadrature axis with respect to Vt. So unless we know the direct axis and quadrature axis, so we cannot determine ID and IQ. So we cannot draw the phasor directly. So what can be done? One of the method is this, that is this is Vt, Ia, theta, this we know. So draw IARA. So from the tip of IARA phasor, this line is drawn which is perpendicular to Ia. So it cuts this line OD at this point. Up to this point, say OB, define it is at EF dashed. Now Vt plus IARA plus AB now is equal to EF dash. Now this AB is perpendicular to current IA. So let us define that it is equivalent to some inductive drop, say IAX, TIAX. X is unknown, we do not know. So from here that you can, this angle is delta plus theta. So these are rectangular triangles. So this is 90 minus delta plus theta. So this is again a rectangular triangle. So again this will be delta plus theta. So from there we have AC. AC is equal to AB cos of this angle, cos of delta plus theta. So this is XIA. So XIA cos of delta plus theta is equal to AC. So that is equal to DE also as per the figure. Now D is equal to ID into XQ. So, and again, this is Ia into cos delta plus theta. Now, Ia into cos delta plus theta, we have seen this is IQ. So, basically, your AC is equal to x into Ia cos delta plus theta is equal to x into xq as per our assumption. And this is equal to dE, which is equal to xq into IQ. So we get x is equal to xq. So the reactance x, what we assumed, is not unknown. This is voltage axis reactance xq. So we have the equation EF dashed is equal to VT plus IARA plus J IAXQ. Now in this equation, right hand side VT is known, IA is known, angle between VT IA is known, RA and XQ are measurable, so EF dashed can be calculated. Now once EF dashed is calculated, you can see EF and EF dashed on the same line. So if we calculate EF dashed, we get the angle delta. So once we get the angle delta, we can calculate quadrature axis current and direct axis current, IQ and ID. And EF, from here you can say it is EF dash plus BD. Now BD is equal to AE minus CB. Now A is IDXT and CB is AB sine of delta plus theta. This is XQIA sine of delta plus theta. Sine of delta plus theta is ID. So this is a XQID and this is XDID. So our BD is equal to CD minus CB is equal to XDID minus XQID. So it is xt minus xq into id. So we get ef dashed is equal to ef is equal to ef dash plus bd. So bt plus iara plus j iaxq plus j id xd minus xq. So we can draw the phasor now, and obviously we can calculate a value of ef dash from here or ef from here, and we can calculate the regulation as EF minus VT by VT. However, this regulation calculated from here, this method is not very accurate. It is almost equivalent to the synchronous reactance method for the cylindrical rotor machine. That XQ and XT, what we determine in the laboratory, are unsaturated value. So this will give a large value of regulation. This is pessimistic, but it gives an approximate idea. But whatever regulation method we discussed, among that, the zero power factor method, ASA method, these two are valid for salient pole synchronous machine also. That is because there nothing was assumed related to the constant air gap. So the regulation of a salient pole synchronous machine, if we want to calculate the value, then we can apply either zero power factor method or ASA method. Now, so for what is important is how can we determine XT and XQ. Now, RA can be measured by DC voltmeter ammeter method, as we measure armature resistance of any machine, DC machine or cylindrical rotor machine. But XT and XQ we have to measure. Now, for XT and XQ, the one test which is done is slip test. For slip test, the machine is driven by the prime mover at a speed nearly equal to the synchronous speed, but not synchronous speed, slightly different from the synchronous speed. The field winding is kept open and a positive sequence reduced voltage is applied to the machine. Now the relative, if when we apply a positive sequence voltage, that will armature winding, this is a three-phase winding, it will create a rotating magnetic field. And the rotor, so rotating magnetic field will rotate at synchronous speed. and the rotor is being rotated by a prime mover at a speed slightly different from the synchronous speed. So the speed of the rotating magnetic field and the rotor field are different. So what happens, say for a particular position, when the direct axis and the magnetic field, rotating magnetic field are coincident, then the air gap is small, that is corresponding to the direct axis. Now, as the air gap is small, reluctance offered by the air gap is also small. So under this condition, the now actually under under this test, we are applying a small voltage to the armature and the field is open. So basically, what the machine, the armature winding is drawing a current, which is basically the magnetizing current to create the rotating magnetic field. Now, as it is a magnetizing current, requirement will be depend on the reluctance of the magnetic flux path. Now we have applied a constant voltage, frequency is also constant, so your flux should remain substantially constant. Now when the MF is coincident with the direct axis, a small reluctance is offered by the small air gap along the direct axis. So for to produce a constant flux, the machine draws a small magnetizing current. So current will be small, and but for say for two pole machine after 90-degree, when the MMF is coincident with the quadrature axis, then the air gap is quite large. So the flux should be constant because your supply is constant. So to create the same constant flux with in a circuit which offers a high reluctance, the machine will draw a comparatively larger current. So current will be maximum when for this position. Now about the voltage, here what we have applied is small voltage, that is around 25% of the rated value. Now, so there will be drop in the leads in the connecting wires. So the drop in leads and connecting wires is comparable when the supply voltage is small. So under this condition, when the current is small, drops in the leads and the connections are also small because current is small. So constant voltage minus small drop, voltage will be maximum. So for this condition, voltage will be maximum, current will be minimum. Similarly, for this condition, current is large, so the drop in the leads and the connections are also large. So constant voltage minus large drop, the voltage will be small. So voltage will be small and current minimum and current will be maximum. So basically, the voltmeter and ammeter connected to the supply will fluctuate. So minimum and maximum. So we can measure the minimum and maximum value, and maximum voltage by the minimum current gives you xt or the direct axis reactance, and the minimum voltage by maximum current gives you the quadrature axis reactance. Now we can connect oscilloscope at that then terminal also. If we connect oscilloscope across the field winding, we will see a very small voltage, and the at sleep frequency will be very low because field winding is open, and it is the speed between the field and the rotating magnetic field is the slip speed. So a very low slip frequency voltage is induced in the field winding. And for the armature current waveform, this is the envelope. The then envelope will have the frequency of this sleep frequency, that is of this voltage, and this is basically the supply frequency. So actually this difference is much more. This is 50 hertz, this will be very small. Just I have just drawn for explanation. That is the current wave will be like this. That is the current is maximum in the quadrature axis and minimum in the direct axis. Similarly, voltage wave will be like this: voltage maximum in direct axis, minimum is quadrature axis. So instead of voltmeter ammeter, we can use an oscilloscope also. From there also minimum maximum can be seen. Now this is a circuit, that is we have applied the reduced voltage. We have ammeter, voltmeter. It is rotated by a prime mover and field is open. Now, what happens actually theoretically, we can calculate both XT and XQ from this slip test. But if you say from the calculate, we can calculate from the oscillogram or from the voltmeter ammeter. From the oscillogram, if we calculate V max, V minimum, I max, I minimum, there can be human error. Similarly, if we measure the maximum minimum voltage and current, there also might be human error during taking readings, and also there some error is introduced due to the inertia of the moving part of the ammeter and voltmeter. So to avoid that, only the ratio xt and xq ratio is determined from here. That is, xt is equal to maximum voltage by minimum current. Xq is minimum voltage by maximum current. So correspondingly, we can determine the ratio of xt and xq. So xt and xq ratio will be minimum armature voltage by by maximum current. This is xq by xd. So minimum armature current by maximum terminal voltage. Now there are certain things. One is that during the performing the experiment, the sleep should be small, because the actually this is salient pole machine. So on the pole surface we will have damper winding. So whenever there is a speed difference between rotating magnetic field and the rotor, there will be induced in the induced voltage in the damper winding, and current will flow, which will try to uh, synchronize the rotor. So if the current if the voltage is large, induced current in the damper winding will be large also, and so it will try to it will introduce error in the reading, and it will always try to pull the rotor to synchronous speed, and so introduce error in the reading. And pointers also with swing at a very high speed, so it is difficult to read the voltmeter ammeter readings. Then another point is that the applied voltage should be small, because actually as that apply volt unless the apply voltage is small, it is difficult to maintain a small slip, because the torque is reluctance torque developed will try to pull the rotor to synchronous speed. So the voltage should be small. And another thing is that the terminal voltage is varying basically because of the difference in the meter, difference in the drops in the leads and the connection. And these drops are this voltage will change appreciably only if this drop is comparable to the applied voltage. If that drop is very small, compare if the voltage is large, then this drop will is no longer comparable with the voltage. Then it is difficult to note the reading. So that's why we should apply a small voltage, and we should keep a small sleep. Now, so we determine this xq by xt ratio from here. Now, and xt is determined from open circuit and short circuit data. That is, if we perform open circuit test and short circuit test on a salient pole machine, then what happens? Now, this is the phasor diagram of a salient pole machine neglecting armature resistance Ra. Now, when we perform short circuit test, now as Ra is negligible, we know that short circuit current is lagging the voltage almost by 90 degree. So, this what happens if this voltage is lagging by 90 degree? So, the this id is equal to, from here id is equal to ia sine of delta plus theta, and iq is ia sine cos of delta plus theta, and ef, this ef is equal to vt cos delta plus id xd, and this iq xq is vt sine delta. Now, under short circuit condition, power factor is almost, angle is almost 90 degree, and considering Ra is very less than xt xq, we can neglect Ra. If we neglect Ra, then one thing from these equations, you see that for under short circuit Vt is 0. So Vt sine delta is 0. So Ia xq is 0. Now, Ia xq is 0. Xq is a parameter of the machine. Xq cannot be 0. So, IQ should be 0. So, under short circuit condition, IQ is 0. So, we have only ID. So, I short circuit is equal to ID. So, so if we take the ratio of here I have written this should be open circuit voltage. So the open circuit voltage for a field current divided by the short circuit current for a same field current will give you the direct axis synchronous reactance. So actually the open circuit voltage for a particular field current divided by the short circuit current for the same field current give you the synchronous impedance for cylindrical rotor machine. So here we will get the direct axis synchronous impedance. So here I have resistance neglected. So this is XT. Now for the corresponding to the salient pole synchronous motor phasor diagram, actually the same phasor, if we replace I by minus IA, we get the phasor diagram of a motor. So our phasor equation becomes Vt is equal to EF plus IARA plus JIDXT plus JIQXQ. Here also we can draw the phasor in the same way, that is Vt plus Ra. So from here we can draw a line and correspondingly determine the angle delta here for this. So let us see a problem. A salient pole synchronous generator has the following per unit parameters, that is xt is 1.2, xq is 0.8, Ra is 0.025 ohm, all in ohm. No, sorry, this is per unit, all in per unit. So compare the excitation voltage on a per unit basis when the generator is delivering kVA, rated kVA at rated voltage and power factor of 0.8 lagging and 0.8 leading. So our terminal voltage is 1 per unit. So 1 plus J0, taking Vt as reference. So Ia will be 1 angle minus 36.9 for lagging power factor. So 0.8 minus J 0.6. So J in the IAXQ will be J into IAXQ. So this is the value of J into IAXQ. IARA is IA into RA. So EF dashed is equal to Vt plus IARA plus JIAXQ. So adding, we get it is 1.625 angle 22.6 degree. So delta is 22.6 degree. So delta plus theta will be 22.6 plus 36.9, 59.5 degrees. So ID is 0.861 and IQ is 0.507. So our EF will be EF dash plus ID into XD minus XQ. So putting, we get it is 1.9694. So EF will be 1.9694 angle 22.6. Now if it is a leading power factor, IA is 0.8 plus J is 0.6. So similarly we find out JIAXQ. So this is 0.02 plus J 0.015. So EF dashed is equal to VT plus IARA plus JIAXQ. So adding, we get it is equal to 0.9849 angle 50.5. So delta is 50.5, delta minus theta. Here it will be delta minus theta because this is leading power factor. So this will be 13.6 degree. So we get ID and IQ. So EF equal to EF dash plus ID into XD minus XQ. So it is 0.943 angle 50.5. Now this problem, it is for an overexcited synchronous motor, prove that tan delta is equal to Ia into XQ cos theta plus RA sin theta divided by Vt plus Ia into XQ sin theta minus RA cos theta. And XD is equal to Vt sin delta minus IARA sin delta plus theta divided by Ia cos delta plus theta. Now this is from the phasor diagram, this one that we have drawn earlier. This is for the motor, this one. So AB is equal to CD plus AC plus CD is equal to IARA plus IDRA plus IAXQ. So sin delta, we can for sin delta is equal to, just from the phasor we can put the values. Sin delta is AB by OA it is drawn here. Okay. So the first one is AB equal to AC plus AD. AB is equal to AC actually up to this AC plus this CD. This is এখানটা ভুল লিখেছি আমি. So this will be, this is IARA. So this component of IARA, that is along the direct axis, so IDRA plus IQXQ. So this will be C. So sine delta is equal to, this is delta, so sine delta is AB divided by OA, this one. So AB is equal to IDRA plus IDXQ, and OA, this is VT. So this is VT, or VT sine delta is IARA plus IQXQ. Now ID is equal to IA sine delta plus theta, IQ is equal to IA cos delta plus theta. So sine delta, VT sine delta is equal to IARA plus IQXQ. So putting value of ID, this is IA sine RA sine of delta plus theta, and this is IA XQ cos of delta plus theta is equal to, if we can expand this sine delta plus theta and cos delta plus theta, this will be IARA sine delta cos theta cos delta sine theta plus IAXQ cos delta cos theta sine delta sine theta. So we can take all the sine delta terms and cos delta terms on two sides. And from there we get tan delta equal to sine delta by cos delta. So this is IARA sine theta plus IAXQ cos theta equal by VT minus IARA cos theta plus IAXQ sine theta. Again, VT sine delta is equal to IARA plus IAXQ. So XT is equal to VT sine delta. VT sine of delta is equal to IDRA plus this will be XQ, IDRA minus IQXQ. So VT sine delta IQXQ, this is IQ. This is double লিখেছি তাহলে X এখানে কিছু একটা ভুল লিখেছি, দেখতে হবে এক্স জাস্ট এটা দেখে ইয়ে করে দেখে নিও এক্স টি এক্স কি কিছু একটা ভুল লিখেছি. So next is the power angle characteristic. We have derived the power angle characteristic for the cylindrical rotor. So similarly it can be derived for the salient pole machine. Now for that we take the approximate phasor diagram, that is neglecting RA. So this is a phasor. So our P, per phase power, can be defined as PD into VD plus IQ into VQ, because power is voltage and the component of current along the voltage. So ID into component of V along ID, VD plus IQ into VQ. Now ID into VD, this is delta, so VD will be VT sine of delta. So ID into VT sine of delta plus IQ into VT cos of delta. Now VT sine of delta is equal to, this one is equal to IQXQ. So IQ is equal to Vt sine delta by xq, and Vt cos delta, this component is EF minus IdXt. So our Id is equal to EF minus Vt by cos delta by xt. So these two values we put in the, this is the power equation, put in the power equation. So this will be Id into Vt sine delta plus Iq into Vt cos delta. So we have EF Vt sine delta by xt plus Vt square into 1 by xq minus 1 by xt sine delta cos delta. That can be written as sine twice delta. So EF Vt by xt sine delta plus Vt square by 2 1 by xq minus 1 by xt sine twice delta. So this has got two components. If you remember the power expression of salient pole machine, this was EF Vt by xs sine delta. So this portion is comparable to that. It has additionally this expression. Now this is basically the reluctance power, that is, this is the electromagnetic power, because if the excitation 0, this power will be 0, and this is the reluctance power. This is developed by the machine due to the difference in reluctance in the direct axis and quadrature axis. So from the expression you can see that even if the field excitation is 0, some amount of power which is equal to the reluctance power is developed by a salient pole machine. So that's why field failure is a very severe fault in case of cylindrical rotor machine, but in case of salient pole machine, that is not that severe, because the machine can withstand, uh, can deliver some amount of power even when the field excitation is 0. Now for maximum power, dp d delta is 0. So differentiating with respect to delta, we get cos delta value like this. So corresponding to this value, the delta, we will get the maximum the power. So if we plot the power angle curve, it has got two component. One is a sinusoid for fundamental sine component, sine delta, and other is a sine twice delta. So these two are added, so the curve is slightly distorted. The peak occurs before 90 degree for salient pole machine. Now, similarly, salient pole machine, this is also a synchronous machine, so it has inherent tendency to remain in synchronism. So, whenever there is some disturbance, the machine will develop synchronizing torque. So, synchronizing power and synchronizing torque. Now, synchronizing power coefficient for synchronous machine is defined as dp d delta. That is also true for the cylindrical rotor. So synchronizing power coefficient for cylindrical salient pole machine will be dp d delta is given by this expression. So for a small change in load, synchronizing power will be synchronizing power coefficient into del delta. So the previous expression, that is Vt by xs cos delta del delta plus Vt square 1 by xt into 1 by xt by 1 by xt cos twice delta del delta. Synchronizing torque will be, this is per phase power, m ps by omega s. So this is the synchronizing torque. So I stop here today. We'll discuss the different synchronous reactance associated with the synchronous machine and how we can measure it in the next class.